Okay, welcome back to video number 2 of conic sections. Like I said, we started with the ellipse, and we're gonna digress to the parabola now because we need to understand the parabola very well, and we need to understand the parabola in rectangular Cartesian coordinates, in polar, how we shift to polar. We're gonna start polar from scratch, and we are also gonna start parametric in the 4th or 5th video. We'll see how that goes. Now, before I start where I left over, in the previous video I misspoke, or I went quickly as usual. At the by the end of the video number 1 of conic sections, I said remember we talked about the auxiliary circle of an ellipse that has the same center as the ellipse. And once we squish it, the horizontal component of the ellipse stays as r, the radius of that circle. However, the vertical component changes to r minus value. It could be like, if r is 5, it could be r minus 1, or r minus 2, or r minus 1.5. And that's fine, that's perfect. This is what I should have said. But at the beginning of the video, I said r minus x. I meant x as an amount, as like an unknown, not as the x component of the r, okay? Just to clarify this. Now let's go back to where we left off last time. And last time we were talking about the general form. And I said capital, please. That's the only thing I'm going to ask you to not memorize, but keep in the back of your mind for all these conic sections: parabolas, ellipse, hyperbola, and a circle. They all start and emanate from this specific formula with capital letter. And I told you the only thing I want you to memorize is A times C. A is not going to be equal to C. That's going to be a common sense for you now because of that squishing of the circle. That A is not equal to C. That means it's not a circle. When the product of A times C coefficients is positive, is larger than 0, we have an ellipse. When it's negative, we have a hyperbola. That's the only thing I ask you to memorize. Now, there's a lot of new terminology. However, I'm cutting a lot of them. And in this second video, I'm going to introduce a lot of new ideas. For those of you who don't know what a parabola is, we're going to talk about the eccentricity again. We're going to talk about the focal length and the focal distance. We're going to talk about a small p and a small a that is different than the a that we have on the major axis. Remember, we talked about the major axis. This is the ellipse. We said we call this the longest diameter, and there is a center in the middle. And equidistant, we have two points of interest, f and f prime, and we said that the whole thing here is small a, which equals the radius of that auxiliary circle. If you draw a circle like this and you squish it vertically, horizontally the r stays the small a, and they call that the major axis if it's stretched horizontally. We're going to go back to all of this, but this a here is different than this a here that we're going to talk about, and the role of this a. That's why I don't want you to get confused when you switch. And now we're going to switch to polar, and you're going to see a K and a P and a UP. And so please stick with me if you are to study with me or to follow me. And know that the only thing in this second video now that I'm going to ask you to not memorize for now, but for the future it will become like second nature to you, is small p, because we're going to talk about a big P as being a point on the coordinate plane. The small p, or the focal length or the focal distance, which we will define, is equals to 1 divided by 4a. A being that coefficient in front of the squared variable that in those problems where you had the projectile and were launching a rocket or a ball going in the air, bouncing, falling down. This A, when you saw something like in your math or physics math word problem equal minus 1 over 16x squared, and since this minus 1 over 16 is negative, because of that, the parabola opens downward, and and everything works fine and dandy. That's the A that we're talking about here in the parabola. And the small p, we're going to talk about a big P and a small p. The small p is the focal length, or the focal distance in a parabola. We will define in a second. But now, most of you have seen the parabolas, in that form, in the math and physics word problem. Y equal minus 1 over 8x squared plus 3 or plus 5 or plus whatever, it's just the constant after that. How is that, how is a form like this related to the original form, which is the one that we introduced in the first video, the one that has the capital A, and we explained extensively why there is no capital B, why this B times the XY component equals 0. Okay, so we're gonna, after this video, you should be able to switch, and even with the next video, we will also talk about it, keep talking about it. How, are any form, when you see the parabola written in a form like this is the form y, I don't have any more space here, I need my space, y equal a x minus h squared plus k. How is that form related, or how do I derive this form from the general form? Okay, so I'm going to give you a parabola. We're going to start off with a parabola written in that general form. And I chose a simple one that we're going to work with in this video and the next video. X, and even I think in video 4, we will keep working on it. X squared minus 4x plus 20 minus 8y. So I look at the squared component, and I see there is only one squared variable, and that means I have a parabola, because if two variables are squared, you either have a circle, hyperbola, or an ellipse. So I eliminated all the other conic sections, and I'm left off with a parabola. So far, very common sense. Now I come and I look at it, and in order for me to get to a form that has x minus h squared, or x squared, equals, the y on the other side, or, having this h and k. H and k is the new, it's not 0, 0, your vertex, your origin, is the new shifted vertex or origin. All I need to do is go back and review, and this is why I call them key starters or key refreshers. You need to review your factoring, you need to review how to factor, you need to review how to complete the square, and we will do all that, separately and extensively if you are to study with me. Now, if I look at something like that and I want to move it and put it as an x component squared equals y on the other side, I look at it and I'm like, I need to complete the square. But before I complete the square, there's an easier trick that you learn. You take, what is that number? Okay, I can break the 20, and that's what I did. But what am I going to break it into? You look at your b, and then you do minus b, so that's minus 4 plus 4 divided by 2, and then you get what? And then you square it, you get 4, so that's a 4. That's why you need a 4. We will repeat that in the key refreshers. So if I break it into 4, I need a 16 and minus 8. And now, since a, the coefficient here, a has to be 1. This is, again, grade 9, grade 10. This is factoring. A equal 1, so I can, think of a times c equaling 4, and a plus c equaling b, which is minus 4. What are the two numbers that do that? Minus 2 times minus 2 is plus 4, and minus 2 plus minus 2 is minus 4. So there you have it, but minus 2 is not the root. It's x minus 2. the root is x equal 2, okay? So x minus 2 times x minus 2 squared equals, I move the y to the other side, 8y minus 16. And now I can divide by 8. Look, if you divide by 8 here, divide by 8 here, and then you move the y to this side, you get y equal 1 over 8, x minus 2 squared plus 2. And there you have it. I have my form that I'm used to, that I see in the math and in the physics books. When you talk about acceleration of gravity, like I said, and those projectiles, and the rocket launched, and the ball going in the air, soccer, basketball, and then, falling down to the ground. That's what you have. You see that. This form emanated and started, has its roots here, okay? And all conic sections. It's called a standard form. It's called a vertex form because you see it has the H and the K, the new vertex. Your vertex here, if you look at it, H, to make this 0, H equal 2, and plus K, and K equal 2. So I have my new origin, my new vertex at 2, 2. And there I have it. And I have the A as positive, so this parabola opens upward, okay? So this is just to give you an idea. We're going to stick with that example, this particular example, y equal 1 over 8, x minus 2 squared plus 2, where the new vertex, the new origin is at 2, 2, and we're going to keep working on that. We're going to get the inverse of it. When we get to polar, we will try to get the polar equation in the polar with the polar coordinate. We're going to get if there are odd, even functions, domain, range, you name it. So we're gonna also write it in the form that is what? That is the quadruple form. I call it the quadruple form. They don't call it the quadruple form. The form that has 4 in it. And we tell me, yes, you've seen those. X squared equal 4py. And you've seen those. Here, let me erase now. We're done with that. Let's erase. In your books, in your textbooks, grade 9 and 10, you have seen the 4 that we're going to talk about. And if we take the vertex at 0, 0, you've seen this written as x squared equal 4py, okay? Right? Open your books, open your textbooks. You see that, 4py. Now, if it's shifted up, you get it like this, x minus h squared equal 4py minus k, okay? I'm just making it easy to show you the 4. Now, if the parabola opens downward like this, you've seen it in your books as x squared equal minus 4py. Where does this 4 come from? That's a major area that we're going to explain. We're going to spend some time on in the next video. Because once you understand where that 4 comes from, you're going to understand the focal distance. You're going to understand the definition of a parabola. You're going to understand the latus rectum that I'm going to talk about in a few minutes. Okay? Now, if it opens to the left or to the right, that's what you get. You get the y squared, of course, just common sense. And yes, again, it's not a function, but it's a quadratic relation, okay, that we need to study satellites and radar dishes. So this one equals y squared equal 4px. And if it's opening leftward, you see it in your books as y squared equal minus 4px. Okay? So you can write it in this form that has the 4 that we're going to spend, 1 hour in the next video explaining this 4 and how we got to this 4, because this 4 is going to explain almost everything for you using the reverse algebraic technique. We're going to get this 4 as, you're going to take this equation, either this one or this one, we will choose one, and we will start with it as a conclusion, and then we're going to do reverse algebraic, so we're going to go backward and prove there is only one hypothesis that fits this description, meaning this 4 needs to exist there. We'll talk in the side, on the side that where the variable, look, it's not squared. Uh-oh, okay. So what's the difference between the P and the A and the 4 and the A and the 4? Why is the 4 related to the P? We'll talk about that in the next video. But now, also in your books, let's go back to so new terminology we have now. We have the focal length, that we will keep talking about it. We have this small p, we have this 4 that we're gonna also explain and spend a lot of time explaining in the next video. But in your books or in many books, they explain also the parabola, scientifically, very swiftly, and they don't really spend a lot of time explaining it. You know that it has the same attribute, the same characteristic of reflection that the ellipse has. Remember when I talked about the ellipse and the ellipse being, I was explaining how the lithotripter system with the kidney stone and the gallstones work. That has the same reflective property. Any ray, like a sunshine ray, like a sound wave ray, any kind of ray parallel to the axis of symmetry, it's gonna what? It's gonna reflect off the surface and straight into the focus. So if the focus is here, any ray, this is your axis of symmetry, that is parallel to the axis of symmetry is gonna bounce off, reflect off the surface, and straight into that focus point or fixed point. This point is fixed. It's a focus point, but it's a fixed point. Remember that. So basically, we're dealing with waves. Remember the shock waves when I spoke about the lithotripter system? Or we're dealing with radar dishes or satellite dishes, There are waves, shock waves, sound waves, sunshine rays, and they're all bouncing off the curve and at different points. So this at different points means the definition, and they're of course, they're bouncing off, reflecting off the surface straight into that focus point. But since they are coming into different points, the word when we say at different points, that means these points, we need to study them as they move. And that's why we use the parabola a lot in calculus. Before you use an exponential function, you start with a parabola in the parametric system and in calculus. So basically, if I am to define a parabola, I would go like this. I would say it's a plane curve formed by a moving point. The point is moving. Now, in most books, this point is called P, but we're going to distinguish it from the smaller p, which is the distance between the vertex and the focus point, and we're going to call it big P with XY coordinates. So it's a plane curve formed by a moving point, this moving point P with coordinates XY, moving so that its distance from a fixed point equals its distance from a fixed line. Distance of that moving point from a fixed point, where is the fixed point? It's the F, the focus. So this PF is equal to its distance to a fixed line. The shortest distance to a line is what? The shortest distance to a line is a perpendicular. So that fixed line should look something like that. And in most books, this is called M. So this PF over PM, or PF equal PM, first of all. So its distance from a fixed point, the focus point, to a fixed line, perpendicular to a line, they call that line a directrix. It directs that point as it moves along the parabolic curve, okay? So new terminology. PF is equals to PM. And if PF equals to PM, what is that ratio of PF over PM? PF over PM as a ratio in itself, this is the eccentricity. This is where we say how uncircular shape is. So eccentricity falls in the essence of explaining what a parabola is. So it is a moving point, and its distance from a fixed line that directs, that's why they call it directrix, this movement, okay? Its distance from that fixed line to a fixed point of interest, which is the focus, is equal. So PF equal PM. And therefore, thus, the ratio of PF over PM, PF, look at it. I drew it here for you. Yeah, I know you can see it here. This is the parabola, this one. I'm sorry, this is the hyperbola. This is the parabola, where the big P is here. PF over PM, PF over PM for a parabola, they're equal, PF equal PM, so that's equals to 1. So how the shape deviates from being a circle is right at that 1. And what does the 1 mean? The 1, and if you study fractions, if you go back to elementary school, 1 means, everything under 1 is going to be a proper fraction. So when we have an ellipse, look, when the P is here, PF compared to PM now, this is the new PM. PF is smaller than PM. Meaning the numerator is smaller than the denominator. Meaning PF over PM, which is what? Which is your eccentricity. How much does a shape deviates from being circular? Is less than 1, but it's of course more than 0 because it's not a circle. And that's how the E of the ellipse falls between 0 and 1. For the hyperbola, if you keep going, you get your P right here, the big P with coordinate xy. And you draw a perpendicular to this directrix, that fixed line, and you see that PF now, the new PF, is larger, bigger than PM. And PF over PM is more than 1. It's an improper fraction, okay? So, again, eccentricity is linked to the definition and to the understanding of what a parabola is. So, a parabola is a plane curve formed by a moving point so that its distance, the distance of that moving point, big P, with coordinate xy, moving its distance from the distance from P to a fixed point, F, point of interest, the focus points where all the shock waves, the sound waves, the rays, bounce and, go straight to. This distance PF equals the distance from that point to a fixed line. The shortest distance is, of course, a perpendicular. That's why PF equal PM. And this in itself, because the directrix directs how that point moves, it also tells us about the circularity. This is exactly where E, eccentricity, equal 1 when you have a parabola. Okay? We can dig deeper into this with calculus and explain why it's linked to circularity, but this is more than enough for now with all this new terminology. Okay? So there you have it. We have a directrix. We have a big P moving point, PF over PM, eccentricity equals 1. This is in line with the definition of what a parabola is. We already figured out why it's between 0 and 1 for the ellipse. You don't need to memorize this. Why it's more than 1 for the hyperbola. You don't need to memorize this again. Okay? So, and then we have our new terminology, which is, we talked about it, and I'm going to keep talking about it. This is a big P, and we have a small p here between the vertex and the focus point. We call that the focal length or focal distance. Length or focal distance, and that's the small p. And this is, the small p is the one that goes in your equation like this, next to the 4py, or y squared in this situation equal 4px. Okay? Having said that and having given you a lot of new terminology, let me switch back here now and let me see what else and how. Here, let's see. Let's switch back to the tablet first. Okay, so what I have here, I have already explained that to you. You see the big P, I put it big capital P right here. It has coordinate x and y, and then pf over pm is the eccentricity, and it's equal to 1. Now, if and again, it's a small p, the focal distance, this is where f is. This is your focus at 0, x coordinate, and p, y coordinate. Why it's only p? Because the vertex now, the new origin is here. It's at 0, 1. So the coordinates of f, focus point, are 0 and p. But it's a small p, okay, that we call the focal distance and the focal length. How are you to remember this? I'm going to give you not a trick, but this is how I remember it. When I came to the United States in the 1990s, I don't have the build for American football, but I used to play in an amateur team as a punter. I used to punt the ball because I grew up playing soccer. But I was studying conic sections and reevaluating them at the same time when I started playing American football. And I got introduced to the idea of a quarterback focusing and throwing that ball in the air, and a receiver coming at a certain point in time and space and catching the ball. So that's in it. And it's, if you look at the trajectory of the American football, it's a downward parabola. And I liked many teams, you know, and I liked many quarterbacks. One of them was the famous Brett Favre, and Favre is a Swiss word that means, that is not, I don't think this is Germanic, how you put Favre, the F and the V together, and it's written like this. So that's how I remember it. I was re-evaluating my parabolas, my focal length, my focal distance, being fascinated by this focus of the quarterback to throw the point to a particular point in space and time. And I used to like Favre. So for me, the focal length, the focal distance, the focal point, this small p, I got my FV. It's between F focus and V vertex. F focus and V vertex. For yourself, if you want to remember it, you can remember it any way you want. You know, if when we study trig functions, some people remember the quadrants and where is my sine positive, where is my cosine positive, by, you know, remembering as all student take calculus, being all A is for all of them in quadrant 1, student S only the sine is positive in quadrant 2, take the tangent, the cot are positive in quadrant 3. I don't go by that, you know, because I go by something like add sugar to coffee, because I like coffee and I've been drinking coffee since I was a teenager. Anyways, so you can come up with any idea to always remind yourself, embedded in your mind, that this small p, it's in a parabola, it's a focal length and a focal distance between that fixed point, the focus. There's no center here. In the ellipse, there was a center. Remember that? Look, not to forget that in the ellipse, we had a center. With the ellipse, we had a center right here. And equidistant from the center, we had two F and F prime. And the slack was also of equal amount because these were equidistant. And this center is also the center of the auxiliary circle that we're going to talk about. And we're also going to talk about concentric circles. And I will remind you of what a concentric circle is. And we're going to explain what a director circle in order to draw the ellipse. But for a parabola, you don't have a center. It's an open curve with a fixed point where all the rays reflect off the surface, go straight into here. They call it in many textbooks center at the focus. So don't get confused, but it's not a center. There's no center here where we say CF is a magnitude. There's no CF as a magnitude here. You see in some textbooks, and that's, I think it's confusing, center at the focus. Okay, so just don't get confused. Now let's go back here, and yeah, Favre, you can come up with your own. Okay, the last thing I want to talk about before we explain it actually in the next video. If you look at this, I did it on the grid here because I want you to see why it's 2p and p. So we agreed that the f is at 0p here. At 0p. Okay? And this is the new origin, so this is minus p. So this directrix, this fixed line, is at minus p. And here I have the big P, right, like this, right here. And I have something called latus rectum. Latus rectum is a Latin word, the same thing, you know, calculus is a Latin word. It means small, tiny stones. And latus rectum means a side that is straight or a line that is straight. It's straight according to what? Parallel according to what? To that directrix, to that other fixed line on the other side of it. And it's part of the curvature or the radius of the curvature. It's part of the radius of the curvature. I will draw it on the board in a second. But if you look here, you see how you have an axis of symmetry here for the parabola, right? And the two endpoints, let's call them P and Q. This axis of symmetry passes halfway through the two endpoints, okay? It passes halfway through the two endpoints. Let me draw all that for you, all new terminology that we're going to explain in the next video with how did we get that 4. Once we explain how we got the 4, you know, you won't need to memorize any of that stuff. Except so far p equal 1 divided by 4a. Okay? So, if I am to draw this like, how do I have it here? Okay, like this and like that, and I have this as p, I have my 2p here, I have a p and a 2p, and this is my new vertex at 0, 1. And this is what the p at 2p now. Look, 2p. I can choose other points, but I'm choosing this one. 2p. And I want to choose this one if I go also another 2p on this side. And I go all the way up to here. Call it q. So now my pq is parallel. I chose it this way. The two endpoints on that chord, PQ, it's perpendicular to the axis of symmetry. This is the axis of symmetry of the parabola. The two endpoints, PQ, forming that chord, PQ, is perpendicular to the axis of symmetry and parallel to that directrix. Now, this is small p, focal length between V and F, Brett Favre. This is my minus p. This is y equal minus p, that fixed line. Remember, it has to be perpendicular. PF here. PF must be equal to PM. And PF divided by PM equals 1 equal eccentricity equals 1. So there is a new addition to this terminology. It's called LR, latus rectum. Latus means side. Rectum means straight. So a line or a side that is straight to that directrix that is, you know, telling us how that point P or Q are going to move along the parabolic path as the rays or as the shock waves or sound waves are going to bounce off and reflect off that surface. So this LR equals 4P. Now I did it on the grid on the tablet, and you see exactly it's at 4P. Now if you take a point here, you still have a chord, but this is not your latus rectum. latus rectum must be perpendicular to the axis of symmetry in a way that it's a side or a line that is straight parallel to the directrix. Okay? So this way, I have a 2p, I have a 2p, I have a 2p, and I have a square. Oh, and I have a 4 here. We will explain how that 4 came into being next to the p. And on the side of the x squared equal 4py here. Now, here, x minus h, what's my h? My hk is at 0, 1. So, minus 0 squared equal 4py minus 1. There you have it. X squared equal 4py minus 1. Okay? So, where did that 4 come from? We're going to explain it extensively in this video or in the next video. But now understand, so I have the directrix, I have the latus rectum, which is a chord, but this chord is perpendicular to the axis of symmetry. Okay? So the two endpoints are equidistant here. Again, so this is 2p, this is 2p, the whole thing is 4p. Well, where did that 4 come from? Coming soon. Just bear with me. Okay? Now, what else do I have here before I start with the 4? Let's see, what else do we have here? Okay, I have it on the grid here again. Did I have you like this? Okay, I'm sorry. If you didn't see that, I will repeat it quickly. The new terminology tells you there is an LR, latus rectum, 4p. I had the screen on my tablet. I apologize. So LR is a chord. So any 2 points, but if you take it like this, it's not going to be perpendicular to the axis of symmetry. It has to be perpendicular to the axis of symmetry, which is in this situation the y-axis. And it has to go through the F, through the focus point. So it has to be perpendicular to the axis of symmetry in its definition. Side, straight, line straight, parallel to the directrix, and passes through F. So if it passes through F and if it's parallel to the directrix, it's a chord that what? That is perpendicular to the axis of symmetry, which is y here. Okay, so I have 2p here, 2p here. The total length, LR, of a latus rectum, this is my latus rectum, it's a chord here, okay, that is perpendicular to the axis of symmetry. The length is 4p. And then my big P, the point here that is of component xy, or coordinate xy, goes for pf. Remember, this is the directrix at the x-axis here. I have p as big P, pf, divided by pm equals 1. Eccentricity is 1. But how did I, and this is what I was talking about when I realized that I had you on the tablet screen. How is that possible? X squared equal 4py. The 4 and the p are on the side of the variable that is not squared. We will explain that in a minute, and we're going to spend a lot of time explaining that, so it will be in the back of your mind. It will come as a second nature. But where is your vertex here? Your vertex is the hk, the new vertex, the new origin is at 0, 1. So if you follow that, this way of writing the equation, you get x minus h, which is 0, squared equal 4p, okay, y minus k, which is what, 1. So that's the equation of this specific parabola. With a lot of new terminology, with your directrix, with your new chord perpendicular to the axis of symmetry through the focus point. That's why it's called latus rectum. It's a weird name, but in Latin it means a side that is straight, that is parallel to the directrix, going through the focus point. Okay? There's one more thing I wanted to add up here. not to be repetitious, not to repeat. With repetition is always great. Yeah. The only thing I wanna, before I end up this video, I just want to remind you that when we speak about, in this situation, it's x squared equal 4py. This small p is the focal length, my FV for me, my breadth fiber going from vertex to focus. Okay, that's the focal length. And this small p equal 1 divided by 4a, so subsequently, a is going to equal 1 divided by 4p. But p is not a, okay? A tells you the concavity. When a is negative, that coefficient in front of the variable that is squared, that means it opens downward. P is the focal length that we use next to the 4, and we're going to explain where the 4 came from. We're going to explain why is it connected to the P. And in this situation, all of that stuff, you know, the only thing you will still need to memorize after the second video will be this P equal 1 divided by 4a, I promise. Okay? And so let's, because the explanation is going to take us some time, let's end up on this note. And in the next video, we will explain the 4 factor and how it's related to P and why is it on the side of the variable that is not squared, while a is on the side of the variable that is squared. Okay, if you pay attention now. Okay, I'll see you in the next video.